we're going to be deriving some of the properties of dot products. So we're going to define that the vector A dot the vector B equals a1 b1 plus a2 b2, where the A vector is defined as a1 comma a2 and the B vector is b1 comma b2. In this case, we're only using 2 dimensions, but all of the calculations that we make could be extended if we added a third term or a fourth term or however many terms that we want to add. So we want to prove 3 things. First, that A dot A equals the magnitude of A squared. Second, that A dot B plus C equals A dot B plus A dot C. And third, that A dot B equals the magnitude of A times the magnitude of B times cosine theta, where theta is the angle between the 2 vectors. So let's start out with our first property. Let's look at what A dot A is. And to start out, we can just plug it into this definition. So that gives A1, and then our B vector is A again, so this B1 is just going to be A1. And then we have plus A2, and once again this B2 is going to become A2 again. And we can simplify this. This is equal to A1 squared plus A2 squared. And now, because A1 squared plus A2 squared is always going to be positive, we can rewrite this as the square root of A1 squared plus A2 squared, and then squared. So in this case, because the inside is positive, the square root and the square will cancel out and we'll just get back what we had originally. And now when we look at this, on the inside, the square root of A1 squared plus A2 squared, well, that's just going to be the magnitude of A. So we know this is equal to the magnitude of A squared. So we proved our first property, A dot A equals the magnitude of A squared. So now let's move on to the second one, that A dot B plus C equals A dot B plus A dot C. So for this property, we're going to again just start out by looking at what our first expression is. A dot B plus C. Well, we can write this out using our definition. We get A1, and then our B vector is B plus C. So in this case, B1 is going to be B1 plus C1 in our expression here. And then next, we have the second component. We're going to again get A2, but then for the second part, we're going to do the same thing as before where we get B2 plus C2, just like that. And now we know that we can distribute this out. So you get A1, B1 first, and then I'm going to take this A2, B2 and write it over here. So you get plus A2, B2. Then we have A1, C1 and A2, C2. So this is our expression for A dot B plus C. And now we can see that we group these terms and these terms together. So these first 2 terms, A1, B1 plus A2, B2, that's just going to be A dot B. So we have A dot B, and then plus A1, C1 plus A2, C2. That's going to be the same, but it's going to be A dot C. And now we've proved our second property, A dot B plus C equals A dot B plus A dot C. So now we just have one more property, that A dot B equals the magnitude of A times the magnitude of B times the cosine of the angle between the vectors. So for this last property, we're going to have to think a little outside of the box, because our original definition of the dot product is only adding and multiplying things. We don't see any cosine or even any angle there. So we're going to have to figure out what to add to our situation so that we can get this cosine of theta popping out. And when I look at this expression right here on the right, this looks very similar to the law of cosines, which says c squared equals a squared plus b squared minus 2ab cosine c, where c is the angle opposite the side c. So when you see ab cosine theta in this expression here, and then we have ab cosine c down here. So maybe we can try to relate these two. But in this case, the law of cosines is about a triangle. So we're going to have to figure out how to take our vectors and get a triangle out of them. So to start, let's draw the two vectors that we have, a and b. So let's say our a vector goes like this, and our b vector, starting from the same place, goes like this. And now, since we want a triangle, we want to draw a third side, and our cosine theta is going to be the angle between a and b. So let's draw in our theta right here. And because we want this theta to be the c in our law of cosines here, we know this opposite side is going to have to be c. And we can write that as a vector as well. In this case, I'm going to draw it so that it goes from the tip of A to the tip of B. And what that means is that we have A plus C is equal to B. And now we can just subtract A on both sides, which gives us C is equal to B minus A. So now we have a definition of C, and we can start to use this law of cosines here on the triangle we've created. So what that gives, first we want C squared. Well, the length of this side, C, is just going to be the magnitude of C. So we have the magnitude of C squared equals, and then we do the same thing for the other two sides. Magnitude of A squared plus the magnitude of B squared minus 2 times the magnitude of A times the magnitude of B times cosine theta. And now we can start to simplify things. But before we do anything else, we want to look at how we can deal with this C squared, because what we want to end up with only has A's and B's. So we're going to have to get rid of this C. Luckily, we know that C is equal to B minus A. Remember that we know A dot A equals the magnitude of A squared. So in this case, the magnitude of C squared, well, that's going to be C dot C. But because C is equal to B minus A, this left side is actually B minus A dot B minus A. And then we can do the same thing with A and B. We know that the magnitude of A squared is A dot A, and then the magnitude of B squared is going to be B dot B. Now what we have here is a dot product where we're adding things together, and now we see that our property 2 is going to come in handy here, because this is actually going to distribute the same way any ordinary algebraic expression would, because of this rule, because this is basically just the distributive property except with vectors. So we can write this as B dot B plus A dot A minus 2A dot B. And you can think of this as being B squared plus A squared minus 2AB, the same way we would distribute this if it was B minus A squared, just as numbers. So now we have B dot B plus A dot A on the left side, and B dot B plus A dot A on the right side. So let's cancel out the B dot B and the A dot A. And that gives us negative 2 A dot B equals negative 2 magnitude of A, magnitude of B, cosine theta. And now we're almost done. All we need to do is cancel out these negative 2's, and that gets us back to the property we want to prove. A dot B equals the magnitude of A times the magnitude of B times cosine theta. So these two definitions, when you first see them, seem very confusing, because how do you just add the components and somehow that's the same as the magnitudes times the cosine of the angle between them? But really the reason that that's true is because of this triangle that we've constructed here. We can take this triangle, use the law of cosines, and then when we distribute out B minus A dot B minus A, this A dot B term pops out, these other terms cancel, and this equation is what we get. So these are some of the basic properties of dot products.